Dr. M. P. Jayaraman is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on geometric function theory. With 14 years of teaching experience, he has handled topics on probability and queuing theory, discrete mathematics, random process, and engineering mathematics. Being a recognized supervisor for guiding PhD and MS students of Anna University, he is the reviewer of the journal Computer Mathematics and Applications. He has also written books on discrete mathematics and has also published papers in 28 international publications, in 4 national publications, and has presented papers in 2 international and in 2 national conferences.
Welcome you all for UGC lecture series in mathematics. In this session, we are going to discuss about quadratic programming problem in detail. First, we introduce the definition of quadratic programming problem and matrix form of quadratic programming problem. Next, we are going to discuss about the Hundaker condition for the given quadratic programming problem. First, let me start with quadratic programming problem. Quadratic programming problem is a concern with a nonlinear programming problem which optimize the objective functions. Here the objective function is in quadratic form with set of linear non-inequality constraints. So, a quadratic programming problem is concerned with a nonlinear programming problem in which the objective function is in quadratic form. The objective function is in quadratic form and objective function together with set of linear constraints. These constraints are of inequality types. So, quadratic programming problem involves the objective function which is in quadratic form together with a set of linear inequality constraints. So, the quadratic programming problem is defined as follows. Let X transpose and C belongs to R power n, Q be a symmetric n cross n real matrix, that is a matrix Q is said to be symmetric if Q equal to Q transpose. So, Q be the symmetric n cross n real matrix, then the problem of maximizing f of x equal to C x plus of x transpose q x subject to the constraints a x less than or equal to b and x greater than or equal to 0, where b transpose belongs to R power m and A is a m cross m real matrix, is called general quadratic programming problem, simply called as GQPP. So, a quadratic programming problem involves a quadratic objective function together with set of a linear inequality constraints. In this QPP, this term x transpose qx represents a quadratic equations. We know very well this x transpose qx greater than 0, then this quadratic form is said to be positive definite. So, if x transpose q x greater than 0, then this quadratic form is said to be positive definite. If x transpose q x greater than or equal to 0, then this quadratic is said to be positive semi definite. Positive semi definite. If this quadratic form x transpose q x less than 0, strictly less than 0, then this quadratic form is said to be negative definite. If x transpose q x less than or equal to 0, then this quadratic form is said to be negative semi definite. Negative semi definite. So, a QPP involves an objective function which is in quadratic form subject to the constraints of a x less than or equal to b. This Q is a symmetric n cross n real matrix. The order of this matrix is n cross n, it is a symmetric matrix. Suppose Q will be represented Cjk, means here Cjk is equal to Ckj, because of symmetricity this condition satisfied. Suppose this q equal to 0, that is a null matrix, then this objective function simply becomes f of x equal to c x. In such a case, the given quadratic programming problem becomes a general nonlinear programming problem. So, a quadratic programming problem involves a quadratic objective function together with set of linear inequality constraints. In this objective function, if q becomes null matrix, then the given QPP becomes a general nonlinear programming problem. A QPP can be written in this matrix form: maximize z equal to summation Cj xj plus of double summation Cjk xj xk, subject to the constraint summation Aj xj less than or equal to bi, I varies from 1 to m, j varies from 1 to n, together with a non-negative restriction xj greater than or equal to 0. Of course, here the bi value should be greater than or equal to 0. So, a quadratic programming problem in matrix form can be written as this way: z objective function of this form subject to the constraints summation aj xj less than or equal to bi, xj greater than or equal to 0. Now, in order to obtain the Hundaker condition for the given quadratic programming problem, first we have to construct the Lagrangian function. For the given quadratic programming problem, the Lagrangian function is L of x comma lambda, which is the objective function, which is of the form summation Cj xj plus of double summation Cjk xj xk minus summation lambda I into summation aj xj minus bi plus si square. This is nothing but the given set of constraints, and minus double summation lambda mj minus xj plus s squared mj. This equation corresponds to non-negative constraints. Given QPP involving a linear inequality constraint summation aij xj less than or equal to bi. Now, this equation can be written as summation aij xj plus si squared, where si is a slack variable and minus bi equal to 0. Therefore, the corresponding Lagrangian function for this constraint is summation lambda I into this equation summation aij xj minus bi plus si squared. Now, the given quadratic programming problem involves the non-negative restriction xj greater than or equal to 0. Now, we rewrite xj greater than or equal to 0 as minus xj less than or equal to 0. Now, by introducing a slack variable s squared mj, this equation can be written as minus xj plus s squared m plus j equal to 0. Therefore, the corresponding term in the Lagrangian function is summation lambda mj into minus xj plus s squared mj. So, the Lagrangian function for the given quadratic programming problem is listed above. We know very well, for a given nonlinear programming problem, the corresponding Lagrangian constraint is fj minus lambda hj equal to 0, where fj is the partial derivative of the given objective function with respect to the decision variable xj, and minus lambda is a Lagrangian multiplier, and h is the given set of constraints. The second Hundaker condition is lambda I h power I equal to 0. The third Hundaker condition is h of x less than or equal to 0. For the maximizing objective function, the third Hundaker condition is h of x less than or equal to 0, and the fourth condition lambda I greater than or equal to 0. So, for a given nonlinear programming problem, this is our Hundaker condition. Now, we try to find Hundaker condition for the given quadratic programming problem using this condition. So, partial derivative of L of x comma lambda with respect to the decision variable xj, that is, this equation gives us Cj plus summation Cjk xk. So, partial derivative of this function with respect to xj gives us Cj plus summation Cjk, j varies from 1 to n, Cjk xk, minus summation lambda I into aij. The partial derivative of this function with respect to x is summation lambda I aij. Then the partial derivative of this term with respect to xj is plus lambda m plus j. So, for the given Lagrangian function, the partial derivative of the variable xj gives us cj plus summation cjk xk minus summation lambda I aij plus lambda mij. We will take this equation equate to 0. Then the second Hundaker condition lambda into h power I equal to 0 for this equation gives us, I will consider this as equation A. Then lambda I h I equal to 0 is lambda I into summation aij xj minus bi equal to 0. Then the same condition lambda I h I equal to 0 for this term gives us minus lambda m plus j xj equal to 0. We take this as equation as C. Then by applying the condition h of x less than or equal to 0 gives us summation aij xj minus bi less than or equal to 0. The third condition we name it as E, lambda I greater than or equal to 0, xj greater than or equal to 0 and lambda m plus j greater than or equal to 0. So, for the given QPP from the Lagrangian function, by applying this condition we have this 5 condition A, B, C, D, E, which clearly written in this one. Equation A is the partial derivative of the function Lagrangian function with respect to the decision variable xj, which is cj plus summation cjk xk minus summation lambda I aij plus lambda m plus j equal to 0. The second condition lambda I h I equal to 0 gives us lambda I into summation of aij xj minus ba equal to 0. Then again apply the same condition lambda I h I equal to 0 for the second constraint, non-negative constraint. We get the condition as minus xj into lambda m plus j equal to 0. Then h of x less than or equal to 0 gives us the equation D, which is summation aij xj less than or equal to ba. Of course, the lambda I, lambda m plus j and xj greater than or equal to 0. Now, by introducing some variable, we can simplify this 5 equation, which can be written in different form. Let us introduce the slack variable si squared, which is greater than or equal to 0 in equation D. So, let me introduce the decision variable si squared greater than or equal to 0 in equation D. This equation D becomes summation aij xj plus si squared equal to b. We name it as equation D dash. So, by introducing the decision slack variable si squared greater than or equal to 0 in equation D becomes summation aij xj plus si squared equal to bi. Now, by taking mu j equal to lambda m plus j, then equation C becomes C dash, which can be written as mu j xj equal to 0. So, by taking mu j equal to lambda m plus j, equation C becomes mu j xj equal to 0. Now, because of si squared greater than or equal to 0 and equation B can be written as, which will write it as b dash lambda I into si squared equal to 0. So, we simplify the given set of Hundaker condition by introducing a new variable, which we call this as slack variable si squared greater than or equal to 0 and mu j equal to lambda m plus j. By introducing si squared greater than or equal to 0, our equation D becomes D dash, which is summation aij xj plus si squared equal to b. By taking lambda m plus j equal to mu j, equation C becomes mu j xj equal to 0, and because of this condition si squared greater than or equal to 0, equation B can be written as lambda I Si squared equal to 0. Let us have a break. Welcome back. Before break, we introduced the notion of quadratic programming problem. Now, with this new notation, the Hundaker condition becomes this, that d becomes d1 summation aj xj plus si squared equal to bi, and the equation b becomes b1, which is lambda I si squared equal to 0, and by taking lambda m plus j equal to mu j, equation c becomes xj plus mu j equal to 0. Now, from equation b1 and c1, we rewrite this equation as summation lambda I si squared, I varies from 1 to n, plus summation j varies from 1 to I varies from 1 to m, j varies from 1 to n, xj mu j equal to 0. From equation b1 and c1, we get this equation. This equation is called complementary slackness equation. Complementary slackness equations. So, for a given QPP, we will obtain the Hundaker condition as the first equation A, then B1, C1, D1. From B1, C1, we will get the complementary conditions. So, from equation B1 and C1, we will get the complementary slackness condition as summation I equal to 1 to n lambda I Si square plus summation j equal to 1 to n xj mu j, which is equal to 0. Now, with the help of this Hundaker condition, we will try to obtain a Hundaker condition for the given quadratic programming problem. Obtain Hundaker condition for the given quadratic programming problem. Maximize z equal to 2x1 plus 3x2 minus 2x1 squared, subject to the constraints x1 plus 4x2 less than or equal to 4 and x1 plus x2 less than or equal to 2, x1 x2 greater than or equal to 0. So, the given quadratic programming problem involving a quadratic objective function with two set of inequality constraints and a non-negative restrictions. Now, by introducing slack variable, we rewrite these two set of constraints into equations. So, the first equation x1 plus 4x2 less than or equal to 4, by introducing the slack variable s1 squared can be written as x1 plus 4x2 plus s1 squared equal to 4. Now, by introducing the slack variable x2 squared in the second set of inequality constraint, this constraints can be rewritten as x1 plus x2 plus s2 squared equal to 2. Now, this QPP involve two set of non-negative constraints x1 greater than or equal to 0 and x2 greater than or equal to 0. x1 greater than or equal to 0 can be rewritten as minus x1 less than or equal to 0. Now, for this constraints, by introducing a slack variable s3 squared, this equation can be rewritten as minus x1 plus s3 squared equal to 0. By making use of the same procedure, the non-negative constraints x2 greater than or equal to 0 can be rewritten as minus x2 plus s4 squared equal to 0. So, by introducing the slack variable s1 squared and s2 squared greater than or equal to 0, these two set of inequality becomes equation 1 and equation 2. Now, by introducing the slack variable s3 squared and s4 squared, the non-negative constraint can be rewritten as equation 3 and equation 4. So, the given equation can be rewritten as this way by introducing the slack variable s1 squared, s2 squared, s3 squared, s4 squared equal to 0. Here the decision variable x1, x2 and all the slack variable si squared I varies from 1 to 4 should be greater than or equal to 0. So, the given set of constraint can be rewritten in this way. Now, for this equation, we will try to obtain the Lagrangian function. The Lagrangian function for this one is L of x s lambda equal to the objective function 2x1 plus 3x2 minus 2x1 square minus lambda 1, where lambda 1 is the Lagrangian multiplier, into the first constraints x1 plus 4x2 plus s1 square minus 4 minus second set of Lagrangian multiplier lambda 2 into this equation, which is x1 plus x2 plus s2 square minus 2 minus lambda 3 into the third equation minus x1 plus s3 squared minus lambda 4 into minus x2 plus s4 squared. So, by rewriting the given set of inequality constraints into equation, we can obtain the Lagrangian function for this problem is this one. The partial derivative of this function with respect to x1, which is dou L by dou x1 and equate to 0, gives us 2 minus 4x1 minus lambda 1 minus lambda 2 plus lambda 3 equal to 0. Then partial derivative of this Lagrangian function with respect to x2, that is dou L by dou x2, gives us 3 minus 4 lambda 1 minus lambda 2 plus lambda 4 equal to 0. Then dou L by dou lambda 1 equal to 0 gives us x1 plus 4x2 plus s1 square minus 4 equal to 0. Then dou L by dou lambda 2 equal to 0 gives us minus of x1 plus x2 plus s2 squared minus 2 equal to 0. Then dou L by dou lambda 3 equal to 0 gives us minus of minus x1 plus s3 squared equal to 0. Then dou L by dou lambda 4 gives us minus of minus x2 plus s4 squared equal to 0. Next, the partial derivative of the function with respect to s1 gives us minus lambda 1 s1 squared equal to 0. Then partial derivative of this function with respect to s2 gives us minus lambda 2 s2 squared equal to 0. Then partial derivative of this function with respect to s3 gives us lambda 3 s3 squared equal to 0. And partial derivative of this function with respect to s4 gives us lambda 4 s4 squared equal to 0. Now, from the Lagrangian function, partial derivative of with respect to decision variable x1 x2, we gives us this one. Partial derivative of Lagrangian function with respect to Lagrangian multipliers gives us this 4 equation. Then with respect to slack variable s1 s2 s3 s4, we are getting this equation. Now, we can rewrite this equation by writing this as 4x1 plus lambda 1 plus lambda 2 minus lambda 3 equal to 2, and this equation as 4 lambda 1 plus lambda 2 minus lambda 4 equal to 3. And from equation this and this, we are getting our s3 squared equal to x1 and s4 squared equal to x2. So, from this equation we are getting our s3 squared value equal to x1 and s4 squared value equal to x2. Now, by making use of this equation in this two equation, this equation can be simply written as lambda 3 into x1 equal to 0, and this equation can be written as lambda 4 into x2 equal to 0. So, by making use of this equation, that is s3 squared equal to x1 and s4 squared equal to x2, these two equations can be written as lambda 3 x1 equal to 0 and lambda 4 x2 equal to 0. Therefore, from the Lagrangian function, the Hundaker condition for the given problem is 4x1 plus lambda 1 plus lambda 2 minus lambda 3 equal to 2, and the second Hundaker condition is 4 lambda 1 plus lambda 2 minus lambda 4 equal to 3, and The third Hundaker condition is x1 plus 4x2 plus s1 squared equal to 4, and fourth Hundaker condition is x1 plus x2 plus s2 squared equal to 2. Now, from the equation we are getting lambda 1 s1 squared plus lambda 2 s2 squared plus lambda 3 x1 plus lambda 4 x2 equal to 0, where lambda I varies from 1 to 4 and xj varies from 1 to 2 and si squared I varies from 1 to 4, all are greater than or equal to 0. So, for the given problem the Hundaker condition is these 5 equation. Here this equation lambda 3 x1 into x1 equal to 0 and lambda 4 x2 equal to 0 is called complementary slackness conditions. Let me recap of the points. A given quadratic programming problem is maximizing the objective function which is in quadratic form subject to the set of linear inequality constraints together with non-negative restrictions. So, a quadratic programming problem can be written as f of x equal to c x plus of x transpose q x such that a x less than or equal to b, x greater than or equal to 0. For the given quadratic programming problem, the corresponding Hundaker conditions are equation A, equation B, equation C, equation D and equation E. The question is, write down the Hundaker condition for the given quadratic programming problem maximizing z equal to 8x1 plus 10x2 minus x1 squared minus x2 squared subject to the constraints 3x1 plus 2x2 less than or equal to 0, x1 x2 greater than or equal to 0. Now, by rewriting this into equation by introducing slack variable and rewriting this non-negative constraints into equation by introducing slack variable, and from that by obtaining Lagrangian function, and we can get the Hundaker condition for the given problem. Thank you.